Hello, it's voiceless me again. I just want to talk you through these notes today about sampling distributions for sample proportions. So yesterday we talked about a sampling distribution when you take a sample repeatedly over and over and over again. For example, at the beginning of class today, I'm going to have everybody take a sample from this bin of orange beads that I've shown you, orange and brown, and you're going to determine the proportion of beads in your sample, and you're going to plot it on a number line. So the number line is going to have what we would call p hat. P hat is the sample proportion. So when you put a hat over the P, it tells you that this is the proportion of success, the proportion of the thing you were looking for, but it came from a sample, as opposed to P, which would be the proportion of success in a population. It just helps us delineate those. So a sampling distribution of P hat, or a sampling distribution of a sample proportion, is if you took every possible combination and you found that proportion. So another way you could look at this is, for example, Reese Pieces. Sorry, I say that wrong, but you just have to forgive me for that. I'm too old to relearn it. They claim that these candies are 50% orange, 25% yellow, and 25% brown. So let's say you want to investigate to see if that percentage of orange is accurate. So you buy a bag of candy and you open it up and you see what proportion is orange. Now, I have an applet that does this. Oh, I got the wrong one up. Hold on. There we go. And so probability of orange, let's say I've got 25 candies in here, and I'm going to have it count the proportion of candies. So I'm going to draw a sample, and it's really cute. It shows this little animation of the candies falling out of here. All right, and so I got 64%. Now that's higher than what I expected, okay? Higher than 50%, which is what I expected. So we want to know, is it unusually high? So if I want to know if it's unusually high, then I would need to check like lots and lots and lots of samples. All right, so I'm going to take the animation off of that. Let's say that I took 100 samples, all right? And again, here's what I'm getting. You know, I've got this distribution, and I keep taking 100 samples over and over and over again, and I get this interesting distribution. So similar to what we saw yesterday, notice that in the middle of this distribution, it appears to be about 50%, which is the true proportion. So the average of all of the sample proportions gives us the true population proportion. Well, the other thing that we see is that it starts to look kind of approximately normal here, okay, which is kind of what we saw yesterday with some of those means. All right, so for example, my population has a P of 50%. I took a sample of size 25. In this one, I got 52%. I would call that P hat. Now, again, the idea of a sampling distribution of P hat is that every single one of these little dots over here would be a P hat value, would be a proportion. So my number line has a proportion instead of a count. So in the last chapter, we were doing counts. In this chapter, we do proportion. So kind of informally, what do we see? It looks approximately normal. Interesting. We know it has a mean somewhere between 0.48 to 0.52. It looks like the values range from 20 to 80%. It's got a range of about 60%. So there's a good deal of variability there. All right. Oh, went too far. Okay, so when the sampling distribution, what we know is the sampling distribution of P hat is similar to a mean that we talked about yesterday, in that P hat is if your sample size is sufficiently large, it's going to look approximately normal. So in order for the sample size to be sufficiently large, we call this the large counts condition. For a proportion, what we basically need is for the sample to be large enough that you could have 10 successes and 10 failures in your sample. So for example, n times p has to be at least 10, and n times 1 minus p has to be at least 10. And as long as that is true for the population proportion that you think is true, then your sampling distribution will be approximately normal. All right, so in here, our example, 25 Reese's candies here, 50% orange in the population. So 25 times 0.5 is 12.5, that's at least 10, and 25 times that 1 minus 1.5 is also 12.5. So this sample is large enough. So that's what I mean. If I take repeated samples of size 25, this sample is large enough that we're going to have an approximately normal sampling distribution. Now, if you get numbers less than 10, what that means is that your sampling distribution is going to be some non-normal shape. It is not going to be approximately normal. And since it's not approximately normal, all that stuff we know about normal distributions from the last sections, we can't use. Okay, so for example here, if my probability of orange was 0.9 and I took a sample of 25, N times P gives me 2.25. That is not greater than or equal to 10. And if I actually run this sampling distribution in my applet, can you see the skew to the right? Okay, which means if it's skewed to the right, I can't use any of my normal distribution business. I can't use norm CDF. I can't use the business with the percentiles, inverse normal, any of that. I'm just lost. Now here, I have that same 0.9, but I've taken a larger sample. This time I've taken 25, and you can see I'm still seeing that right skew, or that left skew, but it is a little bit less pronounced. So N times P greater than or equal to 10, that's 180, that's good. And then N times 1 minus P, that's 10% of that, that's 20, greater than or equal to 10. That tells us that this sample size is large enough that without having to run the simulation, we know that it's going to be an approximately normal sampling distribution. Now, what's cool about this is if we know a couple things. So first off, if your sampling distribution is approximately normal, if you could find the mean and the standard deviation, then you can find probabilities using norm CDF. So here's what we know, that for a random variable, p hat for one population, and this is on your formula sheet, the parameters of this, the mean of p hat is p. Okay, so for example, in our problem down here, if n is 25 and p is 0.5, the mean of p hat should be 0.5, which means if we repeatedly take samples from this population, we would expect to see a sampling distribution that has 50% as the average, because that's the truth. We would expect this to predict the truth. The standard deviation is given by this formula over here. It's p times 1 minus p over n, and you have to take the square root. For right now, just know that this formula is on your formula sheet, and we're just going to fill in the blanks. 0.5 times 1 minus 0.5, which is also 0.5, divided by 25. We figure that out, we get that standard deviation. Now, in order to have that standard deviation formula work, each time you take, since we're sampling without replacement, you have to make sure that you're taking a small sample. We want that sample to be less than 10% of our population. This is called the 10% condition. If you're sampling without replacement, you need to make sure your sample size is less than 10% of your population size. So the difference between sampling with and without replacement is negligible. So even though sampling without replacement isn't independent, we're going to say it's independent enough for us. And that makes this standard deviation formula applicable to our problem. Okay. So the other thing you would want to say, so basically, the way we would interpret this mean is we would say for all random samples of size 25 from this population, the sample proportion of orange candy, don't just say the proportion, because you have to say the proportion of what? Proportion of orange candies, as opposed to the proportion of yellow or the proportion of brown, will have a mean of 0.5. And for all random samples of size 25, the sample proportion of orange candy will typically vary by about 10% from the population mean of 0.5. That would be our interpretations. Okay, so how do we use this then? So the first thing is, you're dealing with proportions if you're in a problem where the variable is categorical. So a polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year college students attend college within 50 miles from home. So the first question I said, what is my variable? So I go up to all these 1,500 college students. There's my sample size. And I say, hey, do you live within 50 miles from home? And they're going to say yes or no. That's categorical. That means we're dealing with proportions and not means. Okay, so it says 35% of them do, so that proportion of success, this is the population. I'm taking a sample of 1,500, and we're assuming that 35% of all college students there. So the first thing I need to ask is this a random sample? Because if I'm not taking a random sample, remember that can introduce bias, so we want that. So yeah, and I know this because they said SRS, simple random sample. The next thing I want to do is I want to say, what's the mean? So I know that the mean of p hat should be equal to p. So the mean of the sampling distribution of p hat would be 0.35, because that's what p is. Is this 10% condition satisfied? So am I less than 10% of my population? Is 1,500 less than or equal to 10% of all first-year college students? That seems reasonable to me. I mean, I don't know what that answer is, but that seems pretty reasonable. So I'm going to say good enough for me. And so now I can find the standard deviation. So I take this standard deviation formula, and I'm going to do p, 0.35, times 1 minus p, 0.65, divided by 1,500, and I get a standard deviation of 0.0125. Now, I've got the mean and I've got the standard deviation, so if I can prove it's normal, I'm right on track. So is the sampling distribution approximately normal? To determine if it's normal, we're going to check to see, is the sample size large enough? And for proportions, we need n times p and n times 1 minus p to both be bigger than 10. I check n times 1 minus p, that's 525, that's bigger than 10. And this is 975, that's bigger than 10. So the sample size is large enough, my sampling distribution is approximately normal. So here's what I can do, I can sketch it. I have a sampling distribution of p hat, we've got p hat down there. P hat. I know that the mean of p hat is 0.35 and the standard deviation of p hat is 0.012. This question says, what's the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value p hat? So I'm going to go within 2 percentage points either direction here. That's going to give me 0.33 to 0.37. Okay, so I go up and down. Those are going to be my lower bound and upper bound. I'm going to pop this in a norm CDF, lower bound, upper bound, mean, standard deviation, and it's going to tell me that there's about a 90% chance of that happening. Okay, so here's another one. It says, the poll ask a random sample of 1,012 U.S. adults, what do they do with the milk in their cereal bowl after they've eaten? P hat is the proportion of people in the sample who drink the milk. A spokesman for the dairy industry claims that 70% of these adults drink the milk. Suppose this is true. All right, so what do we know? Population proportion is 70%. We took a sample of 1,012. Calculate the mean and distribution of the sampling distribution. That means mean of p hat and standard deviation of p hat. So the mean of p hat is p, that's going to be 0.7. Standard deviation of p hat, 0.7 times 0.3 divided by the sample size, square root, gives me 0.014. Now, in order to do this, I got to check that 10% condition. Is it reasonable that 1,012 is less than 10% of all adults? Reasonable to assume. So, for all random samples of size 12, typically the proportion varies by about 0.01 from that 0.7. Now, it says justify that the sampling distribution of p hat is approximately normal. Got its mean, got its standard deviation. Is it approximately normal? So I check my n times p. 1,012 times 70% is big, and so is 30%. Both bigger than 10, so the sample size is approximately normal. So the sample size is large enough, so we can say that the sampling distribution is approximately normal. So calculate the probability that over 67% of the people drink the cereal milk. I want to know what's the probability that if I take a sample, 67% p hat is going to be or more drink that milk. I know the mean, I know the standard deviation, and I know that it's normal because I just proved that it was. So I'm going to do a norm CDF to get that probability. All right, so here is another example just like this. If you read through the question, notice we're going to check. Is it a random sample? Is the 10% condition satisfied? Both of these things allow us to check for this mean and this standard deviation from this particular problem. We can verify if it's approximately normal. After we've checked all three of these things, we can sketch our curve, put our p hat down there, and answer any question we need to about probabilities of a specific value of p hat. Now, if you wanted to verify that something is approximately normal, you may have to do a little bit of checking, and you need to actually show those steps. So here are two problems where all you're asked to do is ask what the shape is. So if your counts both end up being bigger than 10, you say the shape is approximately normal. If any of your counts end up being not bigger than 10, you would say the sample size isn't large enough. The sampling distribution is non-normal. Now, you don't have to say what it is, skewed left, skewed right, bimodal, none of that. You just have to say it's either normal or it's not normal. The other word you want to throw in there is approximately, because these are approximations. It's approximating normal, because what we really have is a binomial sort of situation here. If I wanted to figure out what's the smallest sample size for a proportion that would give me an approximately normal sampling distribution, then I need to figure out what it would need to be for p and for 1 minus p, what that n would be to give me a size bigger than 10. So, for example, if I set that up and solve for my missing variable here, n needs to be bigger than 2,000, and it has to be bigger than 10.005. So it needs to be bigger than 2,000 to make this work. And if you check, you can get those values. Okay? So when you're working on this is really just another way to use our normal distribution to find probabilities so that we can answer those questions. Is this unusual? Are we concerned about this? All right. Thank you.